All right, so this is a totally optional kind of thing. I just want to, if you're a little bit interested, so how did they come up with these magic numbers? Well, somebody had to sit down and just sort of, well, it starts with a little bit of wishful thinking. You would like to be able to factor something. When can you do it? When can you not do it? Um, and then you just play around with the numbers and you collect things and you look for patterns. And then maybe with even more work, you can actually do a full, complete formal proof using like a little bit of number theory. We won't go all the way there, but we will sort of. The goal for this is I want to just write some things down and I want to observe what the pattern is. So the goal is we want to factor a quadratic trinomial with a leading term that is not 0 and it's not 1, so it's legitimate, whole number bigger than 1 in absolute value. And we got a bunch of other stuff here. So how do we deal with that? Well, this is what we want. And we sort of already saw previously that the answer is that A times C has to factor into P times Q, where P plus Q is equal to B. But let's pretend we don't already know that. Somebody had to figure it out. Here's how they would do it. So they would just wishful thinking. Let's take this thing and let's see what happens. Let's suppose we could factor it. What would we have to get? Left-hand side. Well, if the right-hand side and the left-hand side is equal, it must be that the thing we factored it into would take this form. So j times n times x plus m times k times x. Kind of the most important thing is, as usual, what's the power of x? And j times k. So let me just write it as this. So j times n plus m times k is how many x's we have. Well, okay, what if we call this thing p and what if we call this thing q? This is probably hundreds of years ago that they noticed this. Because a lot of people, math is pretty important. People have been working on it for a very long time. We have m, n, j, k. We have all 4 of those, and we have m, n, j, k. Well, that has to be a, that has to be c. Well, here's kind of the coincidence that they notice, oh, hey, p plus q must be equal to b. J times k, well, we've got 4 different letters. I don't like that very much. But what we do notice is that if we call this thing p and we call this thing q, then a times c, just because we've got all 4 letters represented either way. So kind of, this is how people do math. Whoever discovered this for the first time, or I'm sure several different people noticed it around the same time in different locations and compared notes, and they're like, yeah, this checks out. That's probably what happened, but, well, a times c is m times n times j times k. P times q is also m times n times j times k. You just get all 4 things, and then you're like, oh wow, that might be useful. Maybe I should take note of that. And that's it. So sort of the proof that this always works. If you didn't already know that there was an m, and n, and a j, and a k, if you notice that there was a p and a q that do the magic thing, how do you know that it's always going to work out? That's a little bit more complicated, but this pattern is like kind of this little bit of wishful thinking, and then you notice a pattern that drops out. That's like the key insight that shows that maybe you're on the right trail. And then you try it with 100 different polynomials, and it always works for those 100 cases, you really start to suspect that it's a theorem that someone can actually prove. It takes a little bit of number theory. It's a little complicated, but this is how you just sort of push forward and you find a nice observation. And I just wanted to show you that it's really pattern recognition. If you sort of, this is how people discover things, roughly. So I hope some of you found that interesting. This video is flagged as optional, but if you enjoyed it, I'm glad. But otherwise, don't worry about it. So, all right, there it is.